Right, so this is the review for Unit 7, Quiz number 2, which started going over periodic trends. And so at the top of your review, you should have a bullet list of the different topics that are on this quiz. And then there's some example problems, but I'm going to go through all the topics first. You have to know the meaning of all these different terms. Okay, and then what are the trends, and be able to use the periodic table to predict them for what are these different ideas. So remember, atomic radius is just like a radius on a circle. It's from the middle to the outside. Well, for an atom, the middle is the nucleus, and then the outside, they're called the valence electrons. So it's a distance from the nucleus to the valence or outside electrons. Okay, ionization energy is an energy, how much effort do you have to put in to remove an electron? So it's the energy required to remove an electron. Okay, electron affinity, affinity means a liking for. So it is also an energy, but it's the energy associated with adding an electron. So how much is that atom going to like an additional electron? Okay, electronegativity is the relative ability of a bonded atom to attract shared electrons. Okay, so these three things are really very closely related. It's all dealing with how much do the protons in the middle, the pluses, like the electrons on the outside. Okay, it's just you have to know what the differences are and what we're talking about. So ionization energy is straight about taking that electron away. Electron affinity is about adding a new one. And then electronegativity is if you had another atom with pluses and minuses, okay, and they were going to end up sharing electrons, who is going to pull on those electrons harder? Okay, if that electron was shared, who is going to drag that harder? And so it's all about that, those protons, how hard do they pull? Okay, and so electronegativity, it's important that it says relative. Relative is two things in comparison to each other. So who's going to pull harder? And they have to be bonded, which means your noble gases don't have them because they don't ever bond. Okay. Shielding is the number of electrons or the electrons between the nucleus and then whatever you're looking at. Often we're looking at the valence electrons, and they reduce the attraction of the nucleus. They get in between the nucleus and those electrons. And then ZF is effective nuclear charge. It is the protons, which is the nuclear charge, minus the shielding. It's what do those electrons actually feel from the nucleus? So there's the video notes on this, and there was a diagram in your notes where you had to detail ZF and the shielding for each of these electrons. Okay, you have to know the trends for each of these. So atomic radius across the periodic table, elements get smaller. So atomic radius decreases across, and down the periodic table increases. Okay, that is not the reason why for any of these. Down the periodic table, why the atomic radius increases is there are more energy levels. Okay, more layers of electrons, and across the periodic table, the reason is you have the same energy levels, but more protons, and so you end up increasing your ZF. Okay, those are the reasons for all of the trends. So you have to know both the trends and the explanations. So ionization energy across the periodic table, this increases. And down the periodic table, it decreases. Okay, and the reason is increasing is you have the same energy levels but more protons. It's going to make it harder to remove. And down the periodic table decreases because you have more energy levels, so those electrons are further and further away. They're easier and easier to take away. Okay, electron affinity across the periodic table, it increases. And just keep in mind, these are usually a negative number, so we say it increases negatively. And down the periodic table, it decreases. And again, it's negatively, so you'll just see that term in the statement that they'll be negative. Okay, but it's the same as ionization energy. It's going to be harder. It's going to be more and more attractive as you go across the periodic table because you have the same energy levels but more protons. And down the periodic table, it's going to be less and less attractive because you have more energy levels. So those are further and further away from that attractive nucleus. And then the last one for electronegativity, across the periodic table, it increases. And down the periodic table, it decreases. And the exact same reason increases because you have the same energy levels but more protons, and decreases down the periodic table because you have more energy levels. Okay. As far as shielding goes, trend-wise, shielding across the periodic table stays pretty constant. And down the periodic table, it definitely increases because you have more and more layers. And so you have more and more stuff in the way. And then ZF across the periodic table increases. That's because the protons are getting bigger and bigger. And down the periodic table, it stays relatively constant. So you should have a periodic table where you are able to label all these trends and have them for you. You do not get to use that. You just get to use a periodic table we've been using all year long on your quiz. Okay. All right. So those are a big part of it. You're going to be able to rank things, compare things based on these trends. Okay. And then the other side of these bullet points is kind of a hodgepodge of different things. Ionic size is the same situation as atomic radius, but we're looking at what happens not to Na, but if you make it an ion, Na plus. What happens to the element? And what if you went from F to F minus when they become an ion? An ion has a charge. And so if you become a positive, a cation, you lose electrons, and so you get smaller because the electrons are on the outside. And if you become a negative ion, an anion, you gain electrons, and so you get bigger. Okay, so there's rankings of the ions as well and their size. Okay, reactivity of groups. We're talking about which groups are the most reactive. Okay, so this is talking about whether they give or get electrons. The most reactive, okay, you have very reactive group 1A and very reactive group 7A or 17. Okay, and then group 2A is also pretty reactive. Okay, these two groups give electrons really well, and this group gets electrons really well. Okay, those are the reactivities, and as far as what they do and how they rank on themselves, the most reactive, they get more and more reactive. Down the periodic table on the left side, they're more likely to give electrons as those electrons are further and further away. And for group 7A, they get more reactive as you go up the periodic table because they're more and more likely to get electrons when those electrons are closer to the nucleus. Okay, the metallic character of elements is just where are the elements metals. And so at the beginning of the year, we learned how the periodic table is divided, that your metals are over on the left and your non-metals are over on the right. And so metallic character, you have more metals over on the left. And if your column switches, if your group switches, the nonmetals are at the top and you get more and more metallic as you go down the periodic table. Okay, the hard ones, multiple ionization energies is a pretty challenging one. Okay, but it goes with our graphs, our photoelectron spectroscopy graphs. Multiple ionization energies is talking about if you had K, and then you went to K plus, and then you went to K2 plus, and then K3 plus. If you're trying to remove multiple electrons, understanding that to take one electron versus two electrons, it gets harder and harder to take electrons away. And there is always a huge difference when you start taking away from different energy levels. Okay, and so if you look at potassium, potassium itself has 4 energy levels and 19 electrons. And so its electron configuration is this. The first ionization energy to become K plus is going to take away the first outside electron. It's going to get rid of that level 4. Okay. when you take away the second electron to try to take away to become K2 plus, you're going to take it away from this 3p. And now you're taking it away from different levels, because you're taking away from 4 in the first one and 3 in the second one. So this would be a lot bigger. Okay, you're going to see that second ionization energy here be a lot bigger. Okay, that is different, let's say, than if we used calcium. So calcium's electron configuration is this. So to go from Ca to Ca plus, you would take it away from this 4s. To go to Ca2 plus, to lose 2 electrons, you would also take it away from this 4s because there were 2 electrons there. Okay, but to take away and become Ca3 plus, you would have to then take the electron away from the 3p, and this is where we would get a lot bigger. Whenever there's a different energy level, it gets a lot. There's a big jump. So you're looking for a big jump when you take it away from an inside energy level, not the valence. And so this is where we see our common ions being made. Okay, calcium usually becomes this charge because that's okay to take away 2 electrons, but not okay to take away 3. And potassium usually becomes just K plus because it's only taking away 1 electron. So that's where the charges that we learned back in the beginning of the year about what electrons that they will take away, the 1, 2, and 3, is because their number of valence electrons. Okay. The bonding based on electronegativity, there's just a little scale that says if the difference in electronegativity, so the difference, that's that delta, difference in electronegativity is greater than 1.7, it's called ionic. If it's between 0.3 and 1.7, we call it polar covalent. And if it is less than 0.3, we call it nonpolar covalent. Okay, it's about how well they share. The photoelectron spectroscopy graphs, those are the graphs with the little peaks. Okay, and you're going to have to use these to identify, and you have to remember on the x-axis is energy, and the y-axis is the number of electrons. Okay, and then the highest energy is always coming from the 1s. So you have to identify where the highest energy is, and that's always 1s. And there's a maximum of 2 electrons in 1s. Okay, and then oxide acidity is just as simple as nonmetal oxides are generally acids, and metal oxides are bases. And oxides are simply elements with oxygen. So a nonmetal oxide would be like carbon and oxygen. So like carbon dioxide is a nonmetal oxide, and this is considered acidic. Whereas a metal oxide, if I picked a metal like sodium and said Na2O, that would be basic. Okay, and then the metalloids down here, those are usually more amphoteric. They can do both. Okay, so like SiO2 would be more amphoteric. Okay, so that is an overview of a lot of notes. And so now the example problems here, we're just going to practice ranking things and explaining things. So I kind of went through quickly all the notes from this little section here. So this is not to be relied on as the pure notes. You need to go make sure that you've heard those notes. If anything I said here was confusing or you didn't hear it in the notes, go back to the actual video notes and reference those. Okay. All right. So we're looking at the periodic table. You'll definitely have access to the periodic table. Okay. Here it says we're supposed to rank the following elements in order of increasing atomic radius. Okay. And we're looking at carbon, aluminum, oxygen, and potassium. Okay, and so if you're just asked to rank them, you don't have to explain them. You want to know your trends. So first of all, atomic radius across the periodic table decreases and down the periodic table increases. And so if we want an increasing atomic radius, we want small to big. That's our increasing. And so we want to look at our general trends. If we want to go small to big, the smallest are going to be over here, and the biggest are going to be over here on the periodic table. So we're asked to go this direction. And so we can look at these elements where I've highlighted and say, okay, the smallest is going to be oxygen, then carbon, then aluminum, and then potassium. Okay, going that way, smallest to biggest. Okay. All right, so if they just ask you to rank like that, that's all you have to do. You don't have to explain them. We're definitely going to have to explain some things. All right, question 2 says to rank the following elements in order of increasing electronegativity. So we need to know the trend. Electronegativity increases across and decreases down. So everything is that pattern except for atomic radius there. And so increasing electronegativity means we're going from low to high or small to big like we just did. Okay, and so if we find sulfur, oxygen, aluminum, and chlorine, okay, this may be a little tough to start with, but we're going from lowest to highest. We should identify that the lowest is aluminum. Okay, and then the next one is going to be sulfur. Okay, and then I have chlorine and oxygen. If you had to dictate which matters more, the across or the up and down definitely matters more than the across. Okay, and so the next one is going to be Cl, and then the biggest is going to be O. Okay, so energy levels is going to be more important than protons there. All right, and then 3 says, what is the difference between electronegativity and ionization energy? Ionization energy is the energy required to remove an electron. Electronegativity is a ranking, so it's a relative ability. So they're compared to each other of a bonded atom to attract shared electrons. Okay. All right. 4 is an actual explanation, not a pattern, a trend. It's telling you what it is. It's just asking why. So it's pointing at fluorine and iodine. And it says, why does fluorine have a higher ionization energy value than iodine? So ionization energy, we did learn that it increases across and decreases down. So that fits with our pattern that said fluorine would have higher than iodine because it's supposed to decrease as you go down. That's not the reason why. We organize them like this. The reason why is about the atom themselves. Okay, so the up and down reasons on the periodic table is about the energy levels. Okay, so fluorine has valence electrons, its outer electrons, in the second energy level. While iodine has valence electrons in the fifth energy level. And ionization energy is about removing electrons. So trying to take an electron away from an energy level that's further away from the nucleus is easier. So removing electrons from energy levels closer to the nucleus, which is what second one is harder than those further from the nucleus. And that's what level 5 is. It's further away. So if you go back to your little drawings that we did, okay, about the atoms themselves, for fluorine, you're trying to take the electron away from level 2. And for iodine, you're taking it away from level 5. And for both of them, the protons are in the middle for either one. And so iodine's is much further away. It's going to be easier to take away. Fluorine's is much closer to the nucleus. And it's asking you to explain that. So it's the difference in energy levels there. Okay, and now 5 is a ranking. So this one has 4 more elements here. Okay, so we're going to look at magnesium, silicon, calcium, and aluminum. And it asks us to rank them by decreasing first ionization energy. So decreasing is big to small. And we go back to our patterns. Ionization energy across increases and down decreases. And so the biggest are going to be over here and the smallest are going to be over here. So if we're going big to small, here's going to be our biggest. Okay, and then aluminum, and then magnesium, and then calcium. Okay, but I do want to go back into this because ionization energy is the one that has a couple weird blips. We looked at in the notes where we said it should be increasing going a certain way, but we saw that actually there's two little anomalies here. So we're going to end up switching some things around. And so the anomalies happen when you switch from the S to the P or the P3 to the P4 when we were doing electron configurations. And so if you look at where magnesium is, okay, these two right here, it should be increasing there, but that's where we see that little dip. And so these two actually get switched around. That is a pretty difficult concept. Okay, but we see that happen in nature. We can't argue with it. We just had to figure out and explain why, that there's must be something different about S's than P's. Okay. All right. Then for 6, it's not a multiple choice question. Okay. It is an actual 6 different questions, and we're trying to circle in each one. Okay. So it says for the following pairs of atoms and their corresponding ions, determine which one is larger. And so we talked about above. Okay. If you're becoming a cation, you're losing electrons, you get smaller. And if you are gaining electrons, you're becoming an anion, you get larger. Okay, so out of each of these, you have to pick the smaller one or the larger one. Okay, for Na and Na plus, Na's got to be larger because Na plus got smaller. Ba2 plus and Ba's got to be larger because Ba2 plus lost electrons, it has to be smaller. O versus O2 negative, the larger one has to be O2 negative. If you gain electrons, you get larger. D has to be Cl negative because you gained electrons, you got larger. Al has to be bigger than Al3 plus because 3 plus got smaller, it lost electrons. And N3 negative has to be larger, it gained 3 electrons. Okay. All right. And then we are ranking 4 more elements here. All right. We're looking at germanium, phosphorus, strontium, and cesium. Okay, and we're asked to rank them in order of increasingly negative electron affinity. Just remember, you're going to see that with electron affinity. So electron affinity increases as you go across and decreases as you go down. And they just are going to be negative. So you're going to see that. You don't have to do anything with that. Okay, so if we're going to go increase in our negative electron affinities, we're going from small to big. Okay, so the smallest are going to be down here, and the biggest are going to be up here. So we're going this way. And so if you look at our elements on the periodic table, okay, we should end up with cesium, and then strontium, and then germanium, and then phosphorus. Okay. Number 8 asks us to explain, why does atomic radius generally decrease as you go across a period on the periodic table? Okay, and this is where they asked us to explain it. Okay. Okay, in the same period, the elements have the same number of energy levels, but protons increase across from left to right, and the protons attract the electrons better, pulling in the valence. Okay, they drag that last layer in better the more protons you have. All right, and then 9 has 4 questions just based on the same 4 elements, asking different ideas about them. So we're going to look at lithium, beryllium, sodium, and magnesium. I'm going to try to get that out of the way for us. So we're at lithium, beryllium, sodium, and magnesium right here. Okay, and we're asked which element has the highest first ionization energy. So remember, ionization energy increases across and decreases down. So the highest ionization energy should be top right. So BE. And the reason why is not because it's top right. Okay, we put it there. Okay, it's because we're trying to take away electrons. It has the fewest energy levels. So those energy levels are closest to the nucleus, and it has the most protons. Okay, so we're saying these both have 2 energy levels, and these both have 3 energy levels. So it's going to be harder to take electrons away from level 2 than it is level 3, because level 3 is further away. And then out of lithium and beryllium, lithium only has 3 protons, and beryllium has 4 protons, so it's harder to take away from beryllium. Okay, I'm going to skip B right now and go to the others for the trends, or C. Okay, and then I'll come back to B and D, which are related. Okay, C says which element has the lowest electronegativity. So electronegativity increases across and decreases down. So the lowest electronegativity should be down here. And so it should be Na. Okay, but that's not an explanation of where it's located. Okay, so electronegativity is about attracting electrons, shared electrons. So why would sodium have the lowest? It has the most energy levels with the fewest protons. Not the fewest protons overall, but out of the 2 that have the most energy levels. Okay, so energy level 3 is going to be less attractive to the shared electrons than energy level 2. Out of level 3, 11 is less than the 12, so it has less protons attracting things. Okay, so that would be Na. All right, so B and D have to do with what happens after you've removed some electrons. And so that messes with our trends. The trends are just based on if they're their original atoms. If you start messing with them, the trends don't work anymore. Okay, and so I'm going to list out the electron configurations for these 4. So lithium, beryllium, sodium, and magnesium. Okay, and then we're going to deal with both B and D here. Okay, so it says which element has the highest second ionization energy. So the trend is only for something called first ionization energy, which is the first electron that we take. And we always would take, the first electron that gets taken is always the outside electron, the furthest one away from the nucleus, because it's going to be the easiest one to take. So the second ionization energy, it says after you've taken one, who's going to be hardest to take a second one from. So if I went through these 4 elements and took a first one, for lithium, I'm going to take the one from 2s, and now there's nothing there, so that's all gone. From beryllium, I'm going to take it from the 2s, and now there's 1 left there. From sodium, I'm going to take it from the 3s, and now there's nothing there. Okay, and from magnesium, I'm going to take it from the 3s, but now there's 1 left. Okay, so this is if you already took 1 electron from each one of these. If they became a positive 1, what would they look like now? Okay, and so then B is asking what happens if, which one's going to be the hardest to take away the second electron from. So I want to know the highest second ionization energy. Who's the hardest to take away second? So for lithium, you would be taking it away from the 1s. From beryllium, you would be taking it away from the 2s. From sodium, you'd be taking it away from the 2p. And for magnesium, you've taken away from the 3s. And so it is hardest to take away from levels that are closer to the nucleus. The lower the energy level is, it's always harder to take away. So the one that's going to have the highest second ionization energy is this lithium. Okay, and the reason why is because the electron comes from level 1, while all the others are from 2 and 3. So it's harder to take it away from level 1 than it is level 2 or level 3. Okay, and then D says which element has the largest ion, and it says use the most common ion for each element. So I want to go back to that and talk about what we see as their most common ions. Okay, for lithium, when we learned its charge is typically Li plus 1, and because it's okay with taking away 1 electron, but not any further. For beryllium, the most common ion we see is plus 2, because it will let elements take away that second electron. For sodium, what we see most commonly is a plus 1, and if you're confused where I'm getting these charges, this is back when we learned the charges of things. This whole column was a plus 1 and this whole column was a plus 2. So lithium is going to be a plus 1 and so is sodium. And beryllium is going to be a plus 2 and so is magnesium. Okay, and the reason why they are is because where the electrons are coming from. So magnesium is going to let you take 2 electrons away because it'll get rid of that entire third level. Okay, so now it wants to know which element is going to be the largest of these 4. Okay, and so the largest ion, we want to have the most energy levels. So it can't be lithium or beryllium because they only have 1 energy level. So the larger one has to be from Na plus 1 or Mg2 plus because they both have 2 energy levels. So out of those two, if they have the same number of electrons, remember these are considered something called isoelectronic if they have the same electrons. Okay, then we have to look at protons. So sodium has 11 protons and magnesium has 12 protons. So they both would have 10 electrons now, but which one's going to do a worse job pulling in those electrons and be larger? Sodium is going to have the largest ion. And why is it? Because it will have the most energy levels. As Na plus 1 with the fewest protons. Okay, those are fairly challenging to understand when you start editing what they are out of their normal trends. Okay. All right, number 10 here, it has, this one's kind of worded weird, and there is going to be one worded like this, so I want to make sure you understood it. It said, predict which atom of the following pairs will have the higher first ionization energy, sodium versus potassium, and sulfur versus chlorine. So if I asked you Na versus K, which one's going to have the higher first ionization energy? Remember, ionization energy increases across and decreases down. So ionization energy highest is going to be over here, and lowest is going to be down here. Okay, so if we look at sodium and potassium, the one that's going to have the higher first ionization energy should be sodium. And then if I said sulfur versus chlorine, we look over on the right side, sulfur versus chlorine, the highest one should be the chlorine. And so it says predict which atom of the following pairs will have the higher first ionization energy. I've picked both of those. So I want to make sure you could pick in the pairs that we're only comparing these two to each other and these two to each other. And if this were a multiple choice question where I gave the answers Na and S, Na and Cl, K and S, and K and Cl, I'm asking who are the winners. And so we said the winners are Na and Cl. We'd pick the one that has both of those as the winners. Okay. And then last question here says rank the following atoms in order of increasing metallic character. So who's most like a metal? So we didn't have actual patterns for this, but in general, remember your metals are over here on the lower left. So metals, it gets more and more metallic as you go that way, okay, to the bottom left. And so if we look at fluorine, and then indium, selenium, and strontium. Okay, if we want increasing metallic character, we want low to high. So high mean most metal, and low mean least metal. So the least metal is going to be fluorine. It's definitely a non-metal. Okay, and then we hit selenium. It's also a non-metal. And then we hit indium, which crosses over that metal thing. And then strontium is going to be the most metallic. Okay, don't get confused by that. It's just most metallic. Okay. All right, so a lot of trends, some explanations, but a lot of ranking things and understanding what are the patterns here that can help us out predict things. But you do have to know why. And it's all about energy levels and protons.